Excellent.
Hello, everyone. Welcome to QuantumGrad's second presentation for the Qiskit Fall Fest of 2024. I'm your host and lead organizer for the event, Zachary Scott Murphy. Today, we have an amazing presentation from Onri J. Benally, the first Native American quantum hardware engineer. As a quick introduction, Onri has been working in the field of quantum computing for a number of years with extensive experience in the study of quantum chips. Onri's expertise in material physics is impressive, working on state-of-the-art batteries which developed into work on quantum chips with companies such as IBM. Onri is currently working towards a PhD with the University of Minnesota and has gotten funding from the National Science Foundation for his work. As such, we can expect an incredible presentation today. Throughout this presentation, you can feel free to ask questions in the chat. We will get these questions at the end of the presentation, so if you have any questions, regardless of your knowledge in quantum computing, please ask away. Now, please welcome Onri for his talk on quantum chips.
Hello, hello. I'm gonna start up the presentation here. Go. Oh, may need to flip the. There we go. That's better. You can see the whole screen though, right? That's it's on there. All right. All right. So thanks for the introduction. And I'm gonna move this. I'm gonna move one little icon over here. Okay. Um, Thanks for having me here today at the Qiskit Fall Fest. And as as we were discussing, this is going to be about quantum chips. Some things to consider, not necessarily everything, because it's going to be rather short. It's going to go like 30 minutes or so. But regardless, I just became an NSF graduate research fellow as of this year, a couple months ago, and uh, I'm here in my office at the University of Minnesota. So let's see here. All right. So I have a little render for you here on the right. This is a dilution fridge setup. This is what you call an XLD, side load dilution fridge. It's made by or manufactured by Blue Force. This is what it would look like if you were to scrap all of the wires out. And well, most of the wires. It's usually uh, quite quite dense with wires at times. And of course, you can play around with the setup. There's so many ways to configure this thing, and there's many other kinds of dilution fridges out there, and this one here is capable of handling like large setup of uh, quantum devices. You can test what you like all the way down to millikelvin temperature. But anyways, that's that for you. And then we're going to talk about some of the background and motivation from a somewhat materials perspective of making quantum chips. And then we're going to talk about some of the key ingredients for these quantum chips that we call thin films, because we typically make them out of thin film materials, not necessarily superconductors alone, but sometimes we make them out of insulating materials and so forth. So we'll talk about some of those things. And then we'll also talk about the differences or the nuances between the chips that are made of these thin films, and then the measurement system itself, which is the dilution fridge you can see here on the right. And then identification, we're just going to point out some of the critical components like the digital and the analog parts. And there's this key word or key theme that's going to be here in this presentation. That's conversion. We're constantly converting one thing to the next. We're converting one signal to another kind of signal, or one kind of information into another, and back and forth. And then the way we achieve that is by applying these filtration components, amplifiers, isolators, and so forth. And then we're also going to talk about the cavity and device setup versus the mixing chamber that has a bunch of chips in it. There's some things to pay attention to. And then we're going to talk about the workflow when we design it, and then go from there to starting to control it in the lab a little bit, not too deep, and then show some layout automation. I was able to do a Blender tutorial early this summer, actually, showing how that's done. And then here's a little poem for you. It's a little informal, but this is a picture of me at the IBM TJ Watson Laboratory in Yorktown Heights, New York. It's the headquarters of IBM Research. And I worked on the dilution fridges in the quantum lab, and worked on the quantum limited amplifier devices, the films, characterizing the films for those devices, and rebuilding and reconfiguring the quantum computing setup, the quantum test setup. And so here's how the poem goes. Imagine it is like playing with Lego bricks, except the bricks are atoms of solids. That's how we build nanotechnology. We play with atoms and we stack them together like interlinkable bricks. Sometimes we can melt those bricks together. This is called diffusion. So we're going to talk about diffusion in a little bit. There's this thing that we call the nanoscale, and generally we consider something that's about 100 nanometers or less to be in the nanoscale. And there are many references that you can see. People typically like to use like the size of certain kinds of bacteria or viruses as a comparison in terms of how close 100 nanometers is to that. And then on the other hand, even though something is, say, for example, 500 nanometers, even though it says nanometers, there's this weird feeling that in the research community that it is not quite the nanoscale. So there's for sure some stories behind why this is considered to be nanoscale, and it mostly points to things like quantum confinement effects, but you can dig deeper into that. Anyways, so the other consideration is that sometimes, even if a thin film structure or a physical structure is 100 nanometers, at least in one of the dimensions, either laterally or vertically, then we can consider it to some extent to be nanoscale. So it could be a thin film that's about the size of maybe 1 square centimeter, or 10 millimeters by 10 millimeters. And perhaps the thin film is 100 nanometers or less than 100 nanometers. Then we might consider some aspect of that if we were to etch certain parts of that structure as a nano device. So you have to be a little careful with that. And then on the other hand, when we want to make devices out of those, then we're just constantly tearing these structures apart carefully, sometimes with some energy beam, like an ion beam. We're using a physical force to cut into it. And other times we want to rebuild it so that we can insulate it. We can add these insulating components for these desired or undesired effects. And so we tend to make these structures out of these solid state materials like metals, insulators, semiconductors even. And sometimes we make them out of other specialty materials that could be similar to a metal, maybe like a half metal or semi-metal, and things like that. And on top of that, we also have this scale bar here for you. So like when we want to build quantum devices, at least in a research laboratory, and rather than something like a manufacturing facility, then we might focus in on something that can produce a device or a set of devices that is not too dense, or is not too complicated, or is not too cost heavy, or it's not too costly, I should say. then in that case, we can kind of look at this thing called electron beam lithography. This is what we call a maskless lithography technique or direct write lithography technique. And so the wavelength of those electrons are small enough that when we aim it or focus the beam onto a photoresist or a polymer on a chip or a wafer, then we can actually confine those structures, lithographically define these structures so that they are well below 100 nanometers. And some of our machines, we can actually get down to about 3 to 5 nanometer resolution with this kind of technique. And so that's just in the research laboratory. You're not trying to produce 1,000 chips or something. You're just making like one sample or a few sets of samples. And then on the other hand, you want to do manufacturing, then you can start to employ something like extreme ultraviolet lithography. Then you can get some really small structures close to this resolution. And because it's done through projection techniques that's well engineered, then you can, of course, manufacture as many chips as you'd like. And so the interesting thing about that is it does require a mask. And of course, we also have the more conventional mask lithography techniques that's done with a longer wavelength of ultraviolet lithography. So that's a little review for you. But anyways, when we think about some extra motivation here in terms of like what's up to date, we can look at this little chart here from Esmati, and this is a little a lay of the land here, a little scatter plot of these different kinds of qubits as they have progressed over the years. And basically, you want to get closer to this viable NISQ zone here, and then get closer and closer to fault-tolerant quantum computing. And that in itself will require some other manufacturing techniques. And you also have to think about the materials aspect, of course. And we're going to have to need or incorporate some sort of memory aspect as well. So we're going to talk about some of those considerations. So in terms of the ingredients for the thin films, we always think about how to stick these materials together. And we call these adhesion layers. And this can be done with a variety of metals. And here's a short list of these metals, like titanium and chromium. These are very common materials that we can lay down onto a substrate on a piece of a crystal. And we can grow it just a few nanometers thick. We could even go down to about maybe 2 or 3 nanometers even. Then you actually can still get some pretty decent adhesion. But most of our experiments, we do like 5 to 10 nanometers. And it's still good enough to allow a piece of material, like for example, you wanted to stick a piece of silicon on top of another piece of silicon, then, or perhaps you want to stick a piece of gold on a piece of silicon, then the gold is not going to stick on the silicon directly. You need some kind of adhesion material. And so we would stick one of these metals here, one of these materials here in between, and then the gold or whatever metal you're trying to stick to or coat onto the crystal will actually stick to it. So I believe there's some chemistry knowledge that you could study to know more about that. It's related to the electron configuration, electron interaction between the materials and things like that. But you can think of some other aspects of making these thin films, which is the diffusion barrier, which is you are trying to prevent something from melting into some other layer. And so we'll show some graphics here in a bit, little animation of what that looks like. And then on top of that, we can use these structures to build what is called a Coulomb blockade. I guess there's a fancy pronunciation called Coulomb blockade. But we would use this to filter or block out some form of charge, a charge that has different types. And then we also can do a polyspin blockade that blocks out the spin information, and the same with a phonon blockade to try to block out these lattice vibrations, these excitations in the crystal. And then on top of that, we can also consider a seed layer. Maybe we want to grow a crystal of a metal in a certain direction with a certain kind of quality, then you might need to apply a foundational seed layer, kind of like building a house. And then the other consideration is providing an annealing technique. It's just you're sort of forcing entropy into a system of, or should I say, a lattice of these of atoms of metal and insulators, and it will try. You can play around with it experimentally in the laboratory and say, what kind of reorganization are we getting in the end? Here's a little picture of what that looks like. Amorphous is typically where we start. It's like it's a random arrangement of atoms. And then on the other hand, if we grow materials in these vacuum chambers, then we can also get polycrystalline structures. Then there's some sort of arrangement here and there, and it's not entirely well organized, but partially it is. And so that's what we call it polycrystalline. It's got many crystalline structures in it. On the other hand, if we have a crystalline structure, we have this nice repeating pattern. And oftentimes having a high crystalline structure leads to a high quality device at the subatomic level. And so that also affects the performance when we build them into larger and larger structures. So usually when the structure is more crystalline, it has better quality, better performance. And on top of that, we wanted to show you this, or I wanted to show you this little diffusion animation. You can think of these tiny little dots here on the screen as atoms. So the atoms, if you apply some entropy or some energy to the system, then they will begin to diffuse into each other. It melts into each other, as you can see here. But that can degrade the performance of a device. And this is relevant for not just classical devices, but also quantum devices. And there are a list of materials that we would use, like certain kinds of metal nitrides usually, or certain kinds of metal alloys you can use that have really good diffusion barrier properties. And you can keep a library of these, and it will prevent this melting from happening, and it will keep this nice divide as you would like. So when we do that, we can start to think about, okay, now we have all these considerations in mind. Now let's think about what we want to do with the qubits, like a physical qubit, for example. And we also need to keep in mind that these physical structures, these qubits, will represent some sort of matrix, and the computation that will come out of it will, or should I say, the quality of the computation often ties into the quality of the device itself. And of course, there's measurement and things like that, but this is also one of the things that's critical to achieving a more accurate quantum system. So, and then on the other hand, there are active and passive error correction techniques, which is more like it related to the encoding and all. But this is again part of the additional considerations when we're building these physical devices. So we have the software layer. Well, this is what we call the quantum stack. There's a software layer on top, and that is, of course, something that contains the algorithms. When you write the algorithms, you draw or create a quantum circuit that has you want it to have a certain outcome, and then everything is something you could access on a laptop or on a server, And on the other hand, we have the hardware section, which has these analog and digital components. So typically, the lower and lower you get to the device themselves, the physical qubits themselves, then you end up with all of these analog structures. It's just continuously analog. So somewhere within this hardware section of the stack, you have to think about how to convert the digital signals coming from this encoded uh, these encoded pulses from the algorithm and convert that into an analog signal. And so this is done here in the hardware layer. And so on top of that, we also have to think about the different sizes of quantum systems. There are systems such as SpinQ from this company called Gemini. Uh, no, it's the SpinQ is the name of the company, and then this product is called Gemini 2. It's it's more of a novelty of in a sense. You could use it for teaching in a classroom or in a laboratory. It can do some form of quantum computation using a nuclear magnetic resonance setup inside of this desktop size machine. And for a couple $1,000, you could do quantum computing at home. You could own a quantum computer. And not necessarily you couldn't necessarily get like a high performance algorithms or like error correction or anything like that, but it's decent as a teaching tool. And then on the other hand, on the opposite spectrum, we have systems that we are moving towards, which is more server farm like or server clusters, where we can link multiple quantum systems together and obtain a large enough resource that we can actually map larger quantum algorithms on, and then do perform the quantum simulation of physical systems and estimation and so forth. So on the other hand, within those quantum systems, we also have to think about the integration aspect. So we have integration and monolithic architectures in classical chips, what we do with semiconductors. And this is something that is also possible with quantum chips as well. We can have quantum integrated circuits. And so these are able to support all of the necessary control components and also contain the conversion aspects. You can stick a digital to analog converter and analog to digital converter on these components or on these different layers, I should say. And then the amplification, you can play around with the amplification and try to integrate it into the quantum chip, or you can separate it and have it on some other part of the mixing chamber and then play around with the architecture. So this is also something to think about. And on top of that, we also have this thing called a flipper zero. I have one right here, actually. This is the 3D printed model of this flipper zero. It's a programmable radio transceiver. That's what it is. And it's capable of, well, see, the bandwidth goes from megahertz frequency range or couple megahertz all the way up to about 1 gigahertz. So hypothetically, if you could bring a qubit down to say a couple hundred megahertz operating frequency, then you could attempt to trigger it with like a flipper zero, for example, just for fun. I'm not sure how exactly that would turn out because this has never been done before, but the idea here is that you have a radio control system here that you can program, and you can put pulses on here. You can also use the spectrometry tools that are available on this little device, and you can send a pulse, a modulated signal down to a single device. You couldn't do it I'm pretty sure you couldn't do it with a large quantum system, but uh, with this kind of setup, hypothetically, if you plugged it into some dilution fridge or dipstick devoir, then in that case, you may end up with a single qubit or maybe two qubit control. But then you'd have to play around with like the readout. I'm not sure how that would what the quality would be like. That's the thing. But it is something to keep in mind. This is as one of the simple ways to set up a quantum system. So that's what that looks like. And of course, there's going to be some amplifiers that you may have to put in there because we need to convert those signals, those very weak quantum signals, into something that's actually detectable on a classical machine like that. And then on the other hand, we also have single qubit control that typically does have a cavity. So the cavity, we could stick one or maybe two or three qubits, physical qubits in there, and then you could do the testing setup. You can also place a test chip, a device under test, maybe like a resonator structure to test some kind of material properties. And then in that case, it's possible with this kind of setup. And then on the other hand, if you want to do something more focused on computation, do logic, bigger, something a bit more beefy and hefty, then the architecture also has to increase the density as well. So these are things that you have to place inside of that quantum system in order to do that. So this is an example of a traveling wave parametric amplifier that I made a tutorial on. Well, I made a tutorial on how to use Blender to generate a quantum chip layout, and it's on YouTube. I can show you some of those details later. But this is what we call a Josephson traveling wave amplifier, or J-TUPA, traveling wave parametric amplifier. And then this performs this mixing operation. You send a signal that needs to be amplified, a very weak signal, along together with this local oscillator or this pump frequency into the device. And then the nonlinearity of these thousands of Josephson junctions, all in series, will take the energy down that waveguide, and it will perform that mixing operation. And then in the end, we'll end up amplifying or adding the amplitude of the signal from that RF or microwave input and mix it together nicely with that weak signal. And so the weak signal turns into a stronger amplified signal in the end. And the main idea with this device is that the longer you make this waveguide here, or the more Josephson junctions you put on here, then you get more amplification. That's the whole idea. That's why we call it traveling wave. And I have another animation I can show you later, which is the working principle of this device. And it goes all the way back to vacuum tube technology, but it's pretty neat. And then on top of that, there are a lot of components you will see like this. It's kind of this T junction with 3 ports on it. There should be a drawing tool on here, right? Yes. Let me put a drawing tool. So if you had some input into this device, then the input might come here, and there would be, well, this is a ferrite disc here. It's like a magnet, and it may deflect the signal in this direction. And if there's anything that goes on in this little circulator device, let me erase this real quick. Okay, if there's anything that goes on in this circulator device, then the magnetic field would just bend it in the other direction. So that's what's going to happen. Or depending on how this is set up, if the signal comes in on this side through this part, it may bend it this way, or depending on the configuration of the magnet, it might actually go bend the signal this way instead. So the consistency of this circulator is there to help you redirect the traffic of the signal. In other words, let me get this thing back to the main screen. Display. There we go. Okay, so in other words, you get this nice little traffic circle. It keeps the signal going in one particular direction, and then uh, any kind of feedback will not end up going up the same line that it came from. That's what that's for. So the other thing we have to consider is the cryogenic effects on the electronics. We have these different effects such as suppressed noise, the reliability, the writing speed, and things like that. And these are all critical when we are designing these devices because we can use them not just for quantum computing, but also for certain kinds of space electronics because, cold, outer space is pretty cold. And then we also have high performance cloud computing resources, other high performance computing that we can think of. And so that brings us to co-integration. We have state-of-the-art systems that have a huge separation between the temperature of the devices that are being tested or being operated on, and then the control electronics, the interface at room temperature. But the idea of co-integration allows us to think about how to bring this electronic interface into the chamber itself, slowly to the mixing chamber of the cryogenic setup, the cryogenic measurement system. And then we can also think about the memory that's going to help us memorize or store the information about the waveform that's going to control a quantum processor. And ideally, within this future perspective, we would like to place some form of advanced random access memory that's compatible with these kind of temperatures and even new quantum materials, and use that as an integrated architecture at somewhat of a compromised temperature, something like 1 to 4 degrees Kelvin, which is still decent. And then on the other hand, you will have dilution fridge measurement systems that are set up like this. Is pretty typical, but this in itself that you can see here is the measurement system. It's got all these amplifier components, and we also have the isolators that we're just talking about. And sometimes the isolator or circulator is what we were talking about, but the isolator, it looks pretty similar. It's just that on one of those ports, one out of the 3 ports will actually have a sort of a dead end. There's a little shunt resistor or something plugged into that end of a circulator, and it will turn it into an isolator. And then whatever signals coming up this channel will more than likely go to this semiconductor amplifier. And if there's anything coming back down, then it would just hit this dead end because that little magnetic field is redirecting it in that direction. So that's another thing to point out. And then usually on the upper end, at the higher temperatures, like 4 degrees Kelvin and up, you would see some sort of a semiconductor amplifier, something like a high electron mobility amplifier or high electron mobility transistor amplifier. And those typically would operate at 4 degrees Kelvin or above. Although there are some other experiments to try to bring them a little bit closer to like maybe 300 millikelvin or so. There's some IEEE papers you can read about that effort. And then, of course, the quantum device is always here at the bottom, somewhere in the mixing chamber. And depending on the size of the dilution fridge, you can have as many quantum devices as you would like. And depending on how many, say, mechanical switches there are in order to connect to the individual sets of devices that you're testing or using for computation. And then here's another set that is also pretty common. I would say not as well known as the dilution fridge setup, but this particular setup has a dipstick, kind of like what you would see in a vehicle. You're checking oil on your truck or your car. You would see a dipstick that will allow you to test how much oil's in there. But this is not for that. This is a dipstick for holding a sample. And if you have a customized cryogenically compatible PCB, printed circuit board, you can put these quantum devices on there and then place it down here at a much lower temperature, something like 4 degrees Kelvin or so. And say you wanted to test out something that's like spin qubits related, which can operate at those higher temperatures, then in that case, you can use this kind of setup. And the other, I would say the drawback would be that the control system tends to lie on the outside of the setup. And if we do end up testing out a more integrated system, then you could try to squeeze all these components like a arbitrary waveform chip and then the memory chip and so forth. You could try to squeeze it onto that one little PCB at the end of the dipstick. And so that's a little preview for you. And then the signals themselves, of course, requires this instruction architecture. So the key thing to keep in mind is that every physical qubit that are in the system have a unique waveform that they're controlled by. You want to achieve a certain outcome, then there's some sort of waveform memory, or in some cases, random access memory, or a hybrid of the two used to memorize the waveform itself, the envelope of the waveform. And usually it's digitized in that case. But there's this thing called an interpolator chip that will help to smooth out the signal with the consideration for like a Nyquist frequency and things like that, so that it is virtually lossless in terms of the shape of the waveform itself. As you can see, it's mostly like a sinusoidal or like a modulated sine wave of sorts. So, and then this is mostly related to my research. Like we have these devices that are tunnel junctions, and the tunneling mechanism in these devices is dependent on the configuration of the electron spin in these metals. So these are usually metals or metallic structures, semi-metals even sometimes. And the spin in these devices, the collective spin of the electrons in these two different layers will allow us to store, well, more like a physical state of these electrons in one direction or another. And so we can use that state to change the resistance. So if the resistance of this device that we measure ends up being really high, then we can encode it as a 1. And if it's got low resistance, not necessarily superconducting, but it's got low resistance, then we can count that as a 0. And then this is consistent over a long period of time. And I didn't write it here, but the memory can contain in this device many decades over. It takes a long time for this bit flip to happen. It's not gonna randomly flip for a very long time. So this is a pretty robust memory, a memory cell even. And you don't need that many memory cells to use this in an memory architecture, which is kind of neat. Although there are error correction setups that might have maybe 2 or 3 of these junctions as a memory cell, but regardless, you could even rely on just a single cell if you wanted. So that's the neat thing. And then the other thing is this tunneling mechanism does not really care about temperature, so you could do it at room temperature. And in fact, we do most of these memory device tests at room temperature, and that's one thing that kind of trips people up a little bit. So here's some of those devices that I made. These are the MTJ cells, the magnetic memory cells, magnetic tunnel junction memory. And then we can also put them in arrays like this. So this is placed on top of a CMOS structure, and then it could be triggered by an array of transistors. And then based on the configuration, which you cannot see, we can perform computational random access memory. So you can do computation on the memory array itself. And so you really get rid of all of the delay, the latency. There's virtually no latency because the cells themselves perform computation. That's the neat part. But we would hope that this is useful in some of the it goes beyond just the emerging architectures. And this is the cross section of what those devices look like. Here's the thing: we can put superconducting materials in this layer of the memory cell, the molybdenum, and this actually enhances the performance of the device because the entire thing is metal. And the other thing is we can actually when we incorporate this into the layer of the stack of this structure, then we can achieve a lower write energy. So here's a little example: the pulse width, the write energy, the magnetoresistance. The lower we put the temperature with these materials, it will actually increase the reliability of this device. And it continues. We've only been able to test it down to 2 degrees Kelvin because we don't have a dilution fridge in my research team. We mostly work on the synthesis and then fabrication and then some room temperature testing. And then the cryogenic testing is more of a new things for us. So that's something that I'm working on in my PhD work. So here's a little map for you of what that looks like in terms of the switching energy. And this is critical because we could most likely use this as a way to support error correction, the future error correction techniques, which will require memory. And these are just a little overview. This is just a little overview of the shadow mask, how that works. We project the deposition of atoms in one direction, and then we project it in the other direction, and then there will be an overlap in which a junction forms. This is pretty typical for producing junctions for transmons, producing transmons. And then this is a shadow mask example. This is what it looks like. It's a top-down view. And then here's a little animation I made for you, which is of the Josephson junction fabrication. You have these metal atoms being deposited in one direction, and then you deposit it in the other direction afterwards in sequence. You can have this overlapping section. And then in between, if you wait for a little bit, then it will actually form that nice little oxidation layer, which is the tunnel barrier. There you go. The tunnel barrier is highlighted here with this little highlight. I'll let you look at it one more time. There you go. Excellent. Okay, here's just an example of what the Josephson junction looks like. The way there are some other ways of fabricating them. You can perform, instead of just a shadow deposition, you could use typical photolithography techniques, conventional photolithography techniques. You can write a direct beam and lithographically define these structures as well. It's also possible. You can play around with the metals. You can play around with crystalline structures, amorphous structures, and you'll realize that after some time, the performance of the device will improve. And this is just a little sneak peek of how we build these junctions together, these resonator structures as well. And we can use Qiskit metal. We write some Python script, and then the Python script will generate this layout, and then we put the layout in a layout design software like KLayout, which is open source. And then after doing some little cleanup, we can actually import it into the lithography system, and it will actually start to produce the chip. And then that's about it. Anyways, there's more on some of my other lectures. You can see what the chip looks like. But this is more of a little sneak peek slash preview of what I call quantum hardware shortcuts. And these are some of the things to pay attention to when you want to learn about quantum computing hardware. And there's a lot of terms in here and a lot of concepts to keep in mind when you want to study quantum computing hardware. There's so much to learn when with every passing year and all the research that's going on, you have to try to stay up to date. But these are probably the most critical ones to keep in mind. And you'll realize that these are all related to topics like material science, engineering, electrical engineering, quantum metrology, quantum transport, electronic design automation, quantum optics, things like that. And then there's some coding topics to pay attention to as well. Here's a little QR code for that. And that's all I have for you today. So thank you very much.
Thank you, Onri. Well, that was a wonderful presentation and very informative and a great insight into materials research for the future of quantum chips. I'd just like to thank everybody watching live and everybody watching in the future. And please stay away for our next upcoming presentations. We'll be announcing the talk from IBMer soon. And Onri, do you have any final closing comments?
Let's see. No, just many thanks.
All right.
I'll be around. I'm usually pretty oh yeah, the other thing is I'm usually pretty active on LinkedIn, and uh other times I make tutorials like the Blender tutorials, for example, for making quantum chips. I will be, generally available there, and it's pretty easy to reach me. It's not that difficult. I do get a lot of messages from some folks throughout the year, so I try to keep up to date with what people are asking. And then the other thing is this coming summer, I'm also planning to do some more Blender tutorials related to the automation design of the quantum chips, and then some other smaller experiments, something called green lithography technology. It's focused on the sustainable aspect of making structures like these quantum chips. So that's something to keep on the lookout.
All right.
Yeah.
Well, thank you. We'll include those links for people to find in the future. And thank you again, Onri. And we'll see everyone next time.